Hi, this is Knud Valdemar from Aarhus Geosoftware. In this webinar, I'll be talking about working with topography in Res3DInv. And today I'll go through the motivation why add topography in Res3DInv. If you have already watched the webinar on topography in Res2DInv, this will be a little bit of a repetition for you because the reasons are pretty much the same. Then I'll show how to add topography to the Res3DInv DAT files. And finally, I will talk about how you can visualize and export the inversion results once inversions have been run with topography. So why add topography? The prime reason for adding topography to your DAT files is that it will actually improve the inversion results in Res3DInv. It will simply make them more accurate because when the topography is not completely flat, this changes the distances between the electrodes and the current flow path between the electrodes as well. So the current will simply flow differently in the ground when there's topography compared to a completely flat surface. And this is modeled in the forward calculations in the inversion, which simply means that you are giving the program more correct information when you add the topography to your data set, and therefore you will get more accurate inversion results. The second reason for adding topography is that it will make the inversion results look more natural. So if you have made a survey in an area with the topography, then the end user, the customer, will also expect the final models to reflect the topography of the area. So when you look at the models, it is easier to relate them to the real world when you have added the topography. And it is also easier to perform interpretation of the models, because then the depth and the elevations will be more correctly corresponding to the real world, and you don't have to do this brain gymnastics of imagining how the data would look with topography, because the topography is already there. Before showing you how to actually add the topography data to the Res3DInv data files, I'll just talk briefly about coordinates. So in a 3D survey, each electrode and each point of the surface has 3 coordinates, an X and Y and a Z coordinate. And I'll start by talking about the Z coordinates, or the elevation coordinates. In Res3DInv, these are measured with the positive direction upwards. This is not always the case in geology and geophysics. Sometimes, for example, in borehole reports, the positive direction is downwards, down into the earth. But this is not the case for Res3DInv, so you have to bear that in mind. And then we have the X and the Y coordinates. So they are the coordinates giving the position on the surface. This can either be global UTM coordinates, or it can be coordinates in a local coordinate system. But one thing to keep in mind is that these can be measured in 2 different ways. One option is ground distances. So that is, you measure the distances along the ground, following the ground, like you would do if you measured them with a tape measure placed on the ground. This is often the case if you work with fixed distance multi-takeout cables. Then you will usually have an takeout for an electrode for every 2 or 5 or 10 or maybe 100 meters, and you will then put your electrode at these locations. So this means that the distance between the electrodes will be this fixed takeout length following the ground. The other option is to use true horizontal distances. So the X and the Y coordinates will be measured along the horizontal plane. So this is what you'll end up with if you measure the distances on a map, or if you, for example, measure them using a GPS receiver. Then the X and the Y coordinates will be true horizontal distances. And you have to tell the program when you put in the topography in some cases if you are using one option or the other. So we'll get back to that later. In Res3DInv, there is quite a lot of different options for adding topography. The most flexible one, and actually the one I will recommend if you only learn one option, then learn that one because it works for nearly all datasets. And it's also the easiest to add because you don't necessarily have to have the elevation of all electrodes in the dataset. You only need a few of them, and then it can interpolate from there if you don't have all of them. So this is the topography in separate list at end of file option. Then there are a couple of special options that I will show you quickly afterwards. It's one option for rectangular grids, then it's different for trapezoidal grids, and finally it's different again for survey with point electrodes. As I said, we'll start out by looking at the topography in separate list option. And as I also said, this is the most flexible option because you can use it with all the data formats in Res3DInv except for the trapezoidal data format. And the good news here is that it's pretty easy to convert the trapezoidal data format into the general array data format. I'll show that on the next slide. So this is really the only option you need to learn. The other nice thing about this option is that there's not a fixed number of coordinates or topography points you need to add. You can just add however many places you have measured the topography in. So you don't need to know the topography of every single electrode. The program will interpolate the topography from the points that you give it. Okay. So let's look at the top of this file. This is a Res3DInv data file that you can open in a text editor. And all data files will consist of a number of header lines. The number will differ depending on which format the data file is in, and then you will have a lot of data lines, one line for each measurement. And you can see here we are now at line 7267. So now we are at the end of all the data lines. So we have the last 3 data lines here. Then you will add a header. In this case, it's a header for topography. So you write topography. Then you will put either a 1 or 2 depending on the surface or horizontal distances. So that was what I talked about before. If you are using surface distances, so distances measured along the surface, you will put a 2. Or if you use true horizontal distances measured with a GPS or on a map, you will put a 1. Then you need 2 more headers, topography in unstructured list and number of topography data points. And after the last header, you put the actual number of topography data points. In this case, it is 121 points that we want to add. Then you have yet another header, which is called topography data points. And then it gives the format of the next lines, so index X, Y, and Z. And then you put all the topography data points. So all the points for which you know the topography you will put in here. So each line will start with an index, which is just increasing 1, 2, 3, and so on. Then you will have the X coordinate, the Z coordinate, and then the X coordinate, the Y coordinate, and then the Z coordinate or the elevation. And the X and the Z coordinate, X and the Y coordinate needs to be the same as in the data lines, and then you add the topography information as the Z coordinate. And in this case, we have 121 pairs of X, Y, and Z coordinates. And after those, you simply end the file with a few zeros like you always do. So that was the most general way of adding topography in Res3DInv. I actually considered only showing this way in the webinar not to confuse people. So if you are happy with this, you don't need to listen for the next few slides. And as I said, it's possible to convert data in the trapezoidal data format to the general array data format, so you can use the option for adding topography that I have just shown you. You do this by reading in a data file, and then you go to File, Data Conversion, Convert Trapezoidal Grid to Arbitrary Electrodes format. And once you have done that, you will selected that, you will be asked where you want to store your DAT file, and then it will be stored in the general array or the arbitrary electrode formats. You can then reload the DAT file, and then you can add the topography in the way I just shown you. So now I'll go on to talking about some of the other options. There is a special format for rectangular grids. So they are the standard grid type, the most simple grid type, where you have a fixed distance between the grid lines in the X and the Z direction. And then in the header, you simply put, okay, I have 11 grid lines in this case in each direction. Then you have the grid spacing here, and you have the data blocks here. And then at the end of the file, after the data lines, you can put this topography header. Again, you put this this flag for surface or true horizontal distances. And then you simply put in the elevations in an 11 by 11 grid in this case. So here you need to know the elevation of every single electrode, and then you put in, for the first line in the X direction, you put in the elevation of each electrode, and for the second line in the X direction, you put in the elevation of each electrode, and so on. And if you have, for example, a 7 by 20 grid, then this block will also be 7 by 20 entries big. And after that, you are simply at the end of the file, where you end the file with a few zeros as always. The next special format is the format for the trapezoidal DAT file. In that format, you add the location of every single electrode in the header of the file. So in this case, we have 14 by 14 lines. And for the first line here, you have 14 electrodes where you give the location of every single one of them. So the first electrode is in 0.0. They are the X and Y coordinates. And then you simply also put in the Z coordinates or the elevation. And in that way, you tell the program the elevation of every single electrode. So again, in this case, if you do it this way, you need to know the elevation of every single electrode. And then there's one last option. This is the data format where you put in point electrodes. So here you both have a non-uniform grid. So in the header, you give the X location of every grid line, you give the Y location of every grid line, but you also say, okay, we have some electrodes that are not falling on the grid lines, so we need to inform the program of these electrodes separately. And you do this by putting in this header, point electrodes outside grid present. Then you give the number of point electrodes, 1218 in this case. And in this case, we use a compressed format for point electrodes. You will nearly always use this because otherwise you have to put in an extra header for every single electrode. There's not really any reasoning in doing that. And then again, it's a question of putting in an index for each electrode. So you number the point electrodes. Then you give the X coordinate and the Y coordinate and the elevation of each of the point electrodes. So this is a good option if you have point electrodes evenly spread out over the entire survey. Then you can give the topography in this way. If you only have a few point electrodes and they are not covering the whole survey, then this is not the best option, because then you'll only be giving the elevation in the locations where you have point electrodes, and then it will have to extrapolate to the rest of the surveys. So if you don't have enough point electrodes, I recommend that you go back and use the the list at the end of the file. So to sum up, the topography in separate lists works nearly all the time, and then you have these special options if you have one of these three data formats. So that is how to add topography to your DAT files. So to run the inversion, once you have added the topography in your DAT files, you just do like you always do. You load the DAT file, you select inversion, carry out inversion, select where to save the inversion, and so on. And then you don't have to do anything differently than you're used to. Okay, so once you have run the inversion, how can you actually use these inversion results with topography? So now you have added the topography data to your DAT file and you have performed the inversion. So what can you actually do with the results afterwards? You have a few different options for visualization. You can use the classic built-in visualization. You can use the new 3D viewer, which is found in newer versions of Res3DInv. And finally, you can export the results for visualization or interpretation in other programs. And I'll just start out by showing the classical built-in visualization. So to do any of these steps after the inversion, you need to go to display mode. You do this by selecting display and display results. Then if you want the classical visualization like this, but with topography, you select display and display model with topography. Then you will be asked which iteration you want to display and how many sections you want to display. So it says 8 here, but I have cut half of them away to make it fit on the screen. So you will only see 4 here. Then you select in which way you want to cut through your inversion result in the XZ or YZ direction. You cannot show horizontal sections with topography because then you cannot see the topography. And then you select whether you want to show the resistivity model or if you have IP data as well, the IP model. And then you select OK, and you will get a display like this. As you can see, you can always also select to display depth slices. The option is down here. So that's the classical built-in visualization in Res3DInv. The next option I will show you is how to display the results in the 3D viewer. And here the results with topography can be quite impressive. So I'll just load a data set and start up the 3D viewer and show you how that looks. So I'll just switch to Res3DInv and show you how this works. So here you have Res3DInv. Then you need to go to the display mode by selecting display results. And then this will open in a new window. Then you have to load the file with your inversion results. So that is an INV file. I have, of course, prepared one in advance that I have here. And you can see here that this is a data file with topography. So once you have read in the file, you select OK. And then you can select display and display model with 3D viewer. So I'll just do that. And again, you can select which iteration to show. I'll just wait a few moments while the 3D viewer starts up. So here you can see the 3D viewer with the model loaded. And when you have both IP and resistivity inversion results, then by default, it will show the IP results first because that's the last iteration. So you can see you can look at the inversion result from different angles. And if I zoom in a bit, you can see that the topography is there and the pink dots, they are the electrode locations. And if I just switch to the resistivity view, you can do this under display, select field IP or resistivity, then it will look like this. And if you want to be able to see the topography more clearer, you can add a vertical exaggeration to the display. You do this in the main tab, where you can exaggerate in different directions. So I'll do it in the elevation direction in this case. You can see now you can really see the topography kick in. And you have a lot of different options in this 3D viewer. If you want to see more of them, I will suggest that you watch the webinar from last week, where I do a bit more detailed presentation of the 3D viewer. And you can find a link for that one on the web page, and I'll also send it out with the follow-up email to this webinar. And then finally, I'll just tell you how you can export the inversion results if you don't want to visualize them in the built-in visualization or in the 3D viewer. You're of course free to export them to visualize them in any other software or programming language that you prefer, or to put them into interpretation software. And the most general export we have is the XYZ export. It is found under File, Model Export, Export Model to XYZ format. And then in this case, you have to remember to select the one with topography. There's also an option to export it without topography. And again, you can select the which iteration to export. And once you have done that, you will get a text file like this, which simply contains the X, the Y, and the Z coordinates of each of the model blocks, and then the calculated resistivity and conductivity, and also the chargeability if you have IP data. And you can then use this for visualization or interpretation in other programs. You can see that there's also a number of other exports to different other programs. There's to the slicer dicer, there's to the ParaView VTK format that you can use with ParaView. And this is also the format that you'll use if you want to import the results into Aarhus Workbench Essentials, which is another software package that we sell. So that was what I have chosen to show you today. Thank you for listening, and now I have time for a few questions.